Hi, welcome back to Calculus. Today we're looking at section 3.6, the chain rule. Now, before we dive in and take a look at what the chain rule is, how it works, and do some examples, I thought this would be a really good opportunity to take a look at composition functions just a little bit before we start. Um, because the chain rule is going to deal with compositions of functions. So when you have one function basically stuck inside of another one. This tends to be something that a lot of people will find to be just a little bit confusing, so I thought we'd play a little game called product or composition. Yay. All right, so the idea here is just very simple. I'm going to put some examples on the board. You can see I've already got two up here. And we want to try and determine, do we have functions being multiplied, or do we have functions that are stuck inside of each other making a composition? So let's take a look. My first example, f of x here is x squared plus 2, all raised to the third power. And now that all raised to the third power should hopefully give it away just a little bit. But basically, if you can find something that you can replace, and so we could write this as, say, u to the third, where u is x squared plus 2, so we have a composition because this u could take the place of that inside. So this is a composition function, this first one, for sure. The second one, however, is a product. We can see our multiplication right there. All right, well, don't worry, we're going to do a few more examples. But a lot of times people get these mixed up. These are probably two of the nicer ones that people do a pretty good job with understanding. We'll get to some harder ones here in just a second. But we want to start paying attention and thinking, am I multiplying things together, or am I putting one thing inside of another? And that's going to be really important. So let's get some more examples. All right, so continuing on with product or composition. I have three examples here on the board. So let's go ahead and get started. First one, f of x is e to the 2x. Now, there is a product here, right? We have a 2 times an x. But the 2 times the x is stuck inside of e to a power, right? We know what the derivative of e to the x would be. Again, I could make a substitution here. If I called u 2x, then this would just be e to the u, and there's my composition. My inside function is this 2x, my outside function is e to the power, and so that's a composition function. All right, what about g of x is equal to cosine of 2x? It's actually almost identical to this last one. This is one that's commonly people make mistakes on. For some reason, people see a product here where there isn't one. Remember, to take a cosine or a sine or any trig function, you have to take the cosine of something. And the something here is the 2x. And so again, if I call that my u, I could write this as cosine of u, where u is 2x. And so that's another composition function because we have a piece where we can make that substitution inside of it, but there's no product here. The only multiplication is the 2 times x, and that's stuck inside of our cosine. Finally, the last example I have for right now is h of x is sine squared x. So this one's a little bit weird because we're not used to seeing maybe these powers on trig functions too often. Just remember, it's worth thinking about sine squared x as being sine of x squared. And I think if you look at it that way, in this form, it's a little bit easier to see that this is actually another composition function. So we have sine of x stuck inside of a squared function. Again, we could call this u squared, where u is the sine of x. And so this is really what we need to start getting good at. We need to start getting good at recognizing these examples where we have a function embedded inside of another function. And if you're really lucky, we'll get, like 2 or 3 of these things all stuck into one. So anyway, let's get into the chain rule, and that'll be on the next board. All right, here we go. Here's the chain rule. As you can see, I have no room for any examples on this board, so we'll have to wait to the next board to start getting into those. But let's just walk through what the chain rule is and how it works. Chain rule says if f of u is differentiable at u equal to g of x. So here we can see we have a function u, or g of x really, buried inside of another function. And g of x is differentiable at x, then the composition function f circle g of x equal to f with g of x stuck on the inside is differentiable at x. And, to the side, f circle g prime of x, so the derivative, alright, here's the fun part, is equal to f prime of g of x times g prime of x. Or if y is equal to f of u and u is g of x, the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. That's a mess, or at least it sounds like it. It's really not too terrible. So basically, I'm going to focus on this part of the definition up here because I think it's the most useful. What it is you take the derivative of the outside function, but you leave the inside function inside of it. Okay, and so we'll see an example here in just a minute. And then you multiply by the derivative of that inside function. And if you had several of these all together in a great big chain, hence the chain rule, you would just keep going down the line. So if there was a third function embedded inside of g, you would leave it stuck here and then multiply by the derivative of that next function. So yeah, you take the derivative of the outside piece, leave the inside piece there, but then you multiply by the derivative of the inside piece. So let's take a look. This will be fun. Okay, so here is our first example of using the chain rule. I have the equation y is equal to the cosine of x cubed plus 2x. Now, the inside piece is really nice here. It's just this set of parentheses. We have the cosine on the outside, cosine of the stuff on the inside. So I called u x cubed plus 2x, and I went ahead and took its derivative. I dropped the 3 down and lowered my exponent to get 3x squared. And then the 2x, again, I dropped the 1 down. 2 times 1 is just 2. And the x disappears. So we get 3x squared plus 2 for that inside piece. So I'm really looking at y is equal to cosine of u. This is the derivative that I want to take. So how does it work? We take the derivative of the outside. What's the derivative of cosine? Negative sine. So I did the negative sine of u. Okay, we just leave what was there inside, and we'll get rid of that u here in just a second, times the derivative of the inside piece. Okay, times the derivative of that u. So the derivative of the outside function cosine, to get the negative sine u, times the derivative of the inside piece. And that's basically our answer. Now we're just going to clean it up. I'm going to get rid of that u. I really want to bring back what u was. U was just this mess on the inside. And then I don't like having the multiplication at the end because it really looks like I should be foiling these parentheses, but I shouldn't. So I bring that out front, and I leave the negative in front of everything. So negative parentheses 3x squared plus 2 times this, oops, forgot to close that, times the sine of x cubed plus 2x. And there we go. That is how you use the chain rule. Isn't that fun? Don't worry, I've got more examples. It's going to be great. Alright, so I have 2 examples on the board. Let's look at this first one. Y is equal to e raised to the sine x power. So my inside function here is the sine of x, right? We have e to something. That something is my inside piece. So I went off to the side. U is sine x. I know its derivative is cosine x, right? Derivative of sine is cosine. So I'm working with y is equal to e to the u. Its derivative will be e to the u times, then, here's that chain rule, right? We take the derivative of the inside piece. And then I just bring these pieces back. So u becomes sine x, and my du is cosine x, and that's it. You can't really make that look any nicer. You could put the cosine x in front if you want. If you do, put it in parentheses just to make sure you don't try and do something else weird. Alright, next example. I want the derivative with respect to x of 9x to the 4th minus 3x to the 5th, all raised to the 8th power. Now this is just a polynomial. If you really wanted, you could expand these parentheses and then take the derivative of the polynomial. But does anybody really want to expand a set of parentheses with an 8th power on it? I don't think so. So I called u the inside of the parentheses. And you can see over here I have u and its derivative. So the derivative at 4 times 9 is 36, and the power goes down to 3. Minus 5 times 3 is 15, and the power goes down to 4. So the derivative then, right, this is really u to the 8th power, so I dropped the exponent and subtracted it by 1, so I have 8 u to the 7th times there's that derivative of the inside piece again. Replace the pieces, my u turns back into 9x to the 4th minus 3x to the 5th, and du comes in over here, and please don't multiply that out, it's really not worth it. Alright, I'm not done. I've got more. We'll see if we can fit this all in one video or not. Alright, I have 3 more examples. One's on the board and the other 2 will be forthcoming. Alright, so I want the derivative with respect to x of 1 over 7x plus 3. Now, you could use the quotient rule on this. Honestly, I don't like the quotient rule. I try to avoid it as much as I can. That's not entirely true, but this is a great place to avoid the quotient rule. So what I did first is I rewrote it. Since all I have on the top is a 1, and that's really simple, I know that 1 over something is the same as that something raised to the negative first power. Right? That's how negative exponents work. So I rewrote it as 7x plus 3 to the negative first. I called the 7x plus 3u. I took its derivative, which is just 7. So there's my derivative on the inside. That's nice. And then I took the derivative. So I didn't write it out in quite as much detail as I did some of the other examples, but I dropped my exponent in front, and I subtracted 1. Be careful with that here. Negative 1 minus 1 is negative 2. I left what was inside, right? There's my u again. And then times du. Clean up the mess. Negative 1 times 7 is negative 7. And this negative 2 exponent brings the parentheses back to the bottom, now with a square on it. And there we go. I really like the chain rule for this kind of problem. I think it's a really nice way to take the derivative. So let's keep going. Alright, here's a weird little example. Let's take the derivative of the absolute value of x. Now, that's a kind of a piecewise function, right? It's going to have different definitions on the left and right, or where x is positive or negative. So one way to think of it is that the absolute value of x is the same as taking the square root of x squared. The square makes x into a positive number, so then when you take the square root, you end up at the absolute value of whatever x was. So I called u x squared, and its derivative then is 2x. And I rewrote this square root as u to the 1/2 power. Okay, so then I took the derivative, I dropped my exponent in front, and I subtracted 1, which gave me a negative half exponent. So I have 1/2 u to the negative 1/2 power times du. I brought everything back. Right, there's my u and my du. And then I cleaned it up. The 2's here cancel each other out, and the negative takes this piece to the bottom. So I get an x on the top, just from there, that's the only thing left. And then instead of having a positive 1/2 exponent on the bottom, I just wrote it as the square root of x squared. And then we said at the very beginning that the square root of x squared is another name for the absolute value of x. So the derivative of the absolute value of x is x over the absolute value of x. And that's a little bit weird, right? If x is positive, it's just x over x, which is 1. And that is the slope of any tangent line for the positive values of x, for absolute value of x. But if x is a negative number, you get negative x over a positive value that is exactly the same, but positive. And so there you go. All right, let's do one more. All right, I've got 1 minute to finish up this last example, so feel free to pause and stare at it a lot. I want the derivative of the sine of e to the x cubed plus 2x power. This one has two parts to the chain rule. So I start by calling u everything inside of the sine. And so I'm changing it to the derivative of just sine of u. But u is e to the x cubed plus 2x, and that is its own chain rule. So I'm really going to call this e to the w. There's my second substitution. So du is e to the w times dw, whatever the derivative of that is. W is x cubed plus 2x, dw is 3x squared plus 2. So make sure you can do those derivatives. So I bring it back. Derivative of sine is cosine, so I get cosine u times du. Du is this mess, so I put in what u is times du, and then I replace my w and dw as well. So take the time to walk through that. Thanks.